So welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Cami, who is a SETI PI, and he also works in Canada at the University of Western Ontario. And Jan did his MSc in physics at KU Leuven in Belgium, and did another master's in astronomy at University of Porto in Portugal, and at Leiden University in the Netherlands. He then did his PhD work at the University of Amsterdam on molecular gas and dust around evolved stars. And he has also then did a postdoc at NASA Ames, where he worked on diffuse interstellar bands and polycyclic aromatic hydrocarbons in space with Lou Amendola. And soon after that, he became a principal investigator with the SETI Institute. And as I mentioned, he's just moved to the University of Western Ontario after that. Jan is also, as he's going to talk to us about today, published a paper in 2010 where he and his group discovered fullerenes, buckminsterfullerenes in space, in science. And as well as following up with that, he's also involved in online spectroscopy databases, including the spectrafactory.net and NASA Ames polycyclic aromatic hydrocarbons IR spectroscopy database. So if you're interested in those, check them out online. So today we're going to hear from Jan about the story of how he and his group discovered the fullerenes in space. So if you'll join me in welcoming Jan.
Thanks, Adrian. Let me start by saying that it's really a pleasure to be here today. I would like to thank Adrian and Frank for giving me the opportunity to talk to you here today. I have the feeling this talk is long overdue. As Adrian mentioned, I joined the SETI Institute already in December 2005. So sure, there have been some missed opportunities there for giving a talk, I think. At the same time, though, by some chance coincidence, the timing for this talk is highly appropriate. As many of you will have heard 2 days ago, there was another NASA press release, this time about the discovery of solid buckyballs in space. I'll briefly talk about that in my talk. And so I'll be talking about space buckyballs, kind of the more outreach type title. The more technical title would be fullerenes in circumstellar and interstellar environments. What I'll be talking about is I'll spend a fair bit of time on introducing you to the Fullerene family, not just buckyballs, but some of related materials that are kind of very interesting and unique. Talk about some of their properties. I'll spend a fair bit of time on then talking about what we have learned from studying these species in space. And one thing that we have figured out is the life cycle of fullerenes in space. We kind of can track that by combining several observations. However, what we see is that there's many surprises, questions, and problems, as it always goes with science. You do one discovery and it leads to many more questions than you can actually find answers, which is great, right? And I'll briefly mention a few things about why I think this is actually a very interesting discovery. There's lots of opportunities for follow-up research and prying open some other related fields. And so the bottom line, what I hope you take home, is that the presence of C60 and C70 fullerenes in space is now firmly established. One of the very unexpected results is that we find these molecules in a neutral state. We would have expected them to be ionized given the typical radiation fields in circumstellar and interstellar environments. They're also fairly cool, and I'll talk a bit about the implications of that. And we're not quite sure exactly how they are formed. It seems that none of the known formation mechanisms works. We don't know for sure what kind of state they're in, and clearly this ties into this solid state buckyballs. And we don't know what the excitation mechanism is. Now, before diving into the science of buckyballs, I should say that on previous occasion, when I was giving a public talk about buckyballs in space, there was this awkward and somewhat embarrassing interaction with one of the members of the audience. I'm sure in this audience that's not going to happen, but I just want to make sure when I talk about buckyballs, I'm not talking about these commercial buckyballs. So no, we did not find toys in space. And no, if we would have found toys in space, I have no idea who would have put them there. Buckyballs, having said that, are actually really fun to play with. There's these spherical magnets, neodymium magnets. Before you run out, some friends from the Bay Area actually gave me some of these. Before you go out and buy them, they are highly addictive once you start playing with them. But I'm not going to talk about these. What I'm going to talk about is something that's often compared to a different sort of toy, a football, or in North America, I should probably say a soccer ball. A soccer ball, this classical black and white type soccer ball, as you can see, is composed of patches of pentagons, shown in black here, and hexagons shown in white here. Now, if you would put a carbon atom at each of the vertices of a soccer ball, and you would then scale it down to microscopic scales, what you would see is that you now have created a molecular structure with 60 carbon atoms that has the exact same shape and structure as one of these soccer balls. This species is called buckminsterfullerene, and because it's made of 60 carbon atoms, it's also referred to as C60. Buckminsterfullerene is a very long name. People have started calling it fullerenes, or just simply buckyballs. These are one of the most stable species of fullerenes. Now, these were discovered in 1985 by, in some serendipitous result. They were actually looking for something else, and these species popped up. And it really was the beginning of an entirely new field in chemistry, and it boosted the nanotech revolution. This discovery was made by Sir Harry Kroto and co-workers in 1985 at Rice University. And it's not only the buckyballs that are important or useful. In fact, fullerenes are now an entire class of molecules, large cage-like molecules purely made of carbon. And all the time you see that they have different arrangements of a certain number of pentagons and hexagons. Here's a C60, here's C70. It's slightly more elongated. That's the other fullerene that we discovered in space. But it can grow much larger. Here's C84, but that certainly is not the largest one. In fact, you can go all the way up to sizes where you can wonder whether you're talking about a molecule or a small dust grain. So it's C60, C240, C540, C960. There's a whole series of spin-offs of these fullerenes. You can make all sorts of other materials starting from fullerenes, or the Fullerene research has actually boosted or resulted in some more discoveries. For instance, it turns out if you take this set of molecules, you can actually put one of these molecules inside the other, pretty much like a Matryoshka doll, and then what you get is what's called a Bucky onion. Okay? People have actually made this in the lab, right? You can do all sorts of amazing things with molecules like this. And actually, this possibility of having a cage in which you can put small atoms or small molecules is actually something which is very interesting. And certainly in, for instance, the medical areas, people have been looking at that. Because if you can put specific radioactive atoms in there, for instance, you can actually deliver drugs at a certain space. You can more easily diagnose certain things. And so one example is something which is kind of referred to as a Bucky bottle, if you want. Scientists have managed to open one of these fullerene cages on the top by the appropriate chemical reaction. You can put in water molecules, and if you then use this other chemical reaction, you can actually put a stop on this open fullerene cage. And it turns out once this phosphate group is in place, no more species can go in or out. And actually researchers have been able to prove that you can trap a single water molecule in these Bucky bottles and stop them, and then you can actually remove the stop again if you want to. So that's kind of fairly recent development. That's what people are looking for. And so maybe it's this sort of science that has resulted in this Belgian beer company that somehow saw a relation between Buckyballs and beer. But then again, it's well known that Belgians see a relation with beer pretty much anywhere. One of the most spectacular spin-offs was carbon nanotubes. Carbon nanotubes are found, for instance, in the soot deposit that you find if you look at the experiments where you also make the fullerenes. You've probably all heard about carbon nanotubes. The way to make them, simply said, is you take a flat sheet of these hexagons, these carbon hexagons. Such a single flat sheet is called graphene. You roll it up into this cylindrical form, and now you have a carbon nanotube. And so carbon nanotubes are quite amazing. They have properties which are highly sought after in the nanotech world. They're stronger than steel. They're as flexible as plastic. They conduct energy better than almost any material ever discovered, and they can be made from unexotic raw materials such as methane gas. Okay, so that's why people have been trying to produce these in a useful way. One such way is something called Buckypaper. This black, what looks like carbon paper, is actually called Buckypaper. It's a whole collection of carbon nanotubes together. This thin sheet is about 10 times lighter than sheet metal, but it's about 500 times stronger than sheet metal. Okay, so at the same time, it conducts electricity and heat much better than any other material. So there's all sorts of promising applications you can think of. For instance, one example would be next generation computer displays. And so certainly on Earth, it has resulted in a whole spin-off of chemistry and nanotechnology. Now, this is called Buckypaper, so by now you may wonder what this Bucky has to do with it. And of course, since we're talking about species or materials here that have very unique sort of properties, you may think that this Bucky is actually Captain America's sidekick, Bucky, with some super properties. However, that's not quite the case. As most of you probably know, these species are called after the quite intriguing person of Buckminster Fuller, who liked to be called Bucky. He was pretty much anything you can think of. He was an architect, engineer, author, designer, inventor, futurist, humanist. He also kept a detailed log of his entire life, pretty much. And in addition to being an architect and an engineer, he started being a bit philosophical and seeing where humanity is and what we have to do. He came to the conclusion that humanity has reached a point somewhere in the 70s where basically the best survival strategy is by cooperation. And so he concluded, well, selfishness is something which is totally unnecessary. We shouldn't go on war. We should all be working together and improve our world. So he was a bit one of the first environmental activists, so to speak. And one of the ways that he drove this message home is through the concept of spaceship Earth, where the whole idea is, you shouldn't try to build massive spaceship and go out in space. Actually, think about it. The Earth is an entire spaceship already with limited resources. That's the key thing about this spaceship Earth. He developed his own language around this, right? Instead of going upstairs and downstairs, he would say outstairs and instairs to kind of say, you go inside the spaceship or outside the spaceship. And one iconical spaceship Earth that he made is this ball here, which is located in Florida in the Epcot Center. The Epcot is short for the experimental prototype of the community of tomorrow, so it's built around the whole idea of sustainability and limited resources as well. This is a geodesic dome, and Buckminster Fuller did much of the mathematical calculations for this structure. And basically, that's kind of the trademark for Buckminster Fuller when we talk about fullerenes. He developed geodesic domes and got all the US patents for geodesic domes. The interesting point about Buckminster Fuller is that as a child, he had very big difficulties with geometry, actually. He had problems with the abstraction of geometry. If a teacher would draw an X on the board to kind of show that's an arrow going inside the board, he couldn't understand actually what that means. So when he was going home, what he would spend most of his time on is actually build small-scale geometric models to make sense of all the geometry classes. And so by doing that, he got an amazing intuition for all these sort of structures. And at some point, he realized that you can make a full dome, not just half a circle, actually an entire ball, from just combining these hexagons with some pentagons. And he realized that it's the pentagons that actually cause the rounding of the dome. That's also the case when you talk about chemistry on the nanoscale. It's the pentagons in these fullerenes that actually make them curve. So if you start from a flat hexagonal surface, you take away one carbon atom, make a 5-ring, a pentagon, then basically thing starts to curl up. And so loosely based on one of his design of these sort of domes, a soccer ball was designed that was used in 1970 in Mexico for the World Cup for the first time. This was called the Telstar ball. It is actually a Buckminster ball, so to speak. This is the first time it was used in the World Cup. It was called the Telstar after this satellite that has some resemblance to a ball in the sense that it's round and it's black and white, I guess. The black patches actually helped soccer players to kind of see where the ball was turning, so that got some advantage to the player. And so the discovery of C60 and C70 was done in 1985. And at that time, if you look at the original Nature paper, it's probably the only Nature paper that really features a picture of a football and the others say in the United States a soccer ball, actually photographed on Texas grass, it even says. And the title of the paper is quite simple. It was C60 buckminsterfullerene. And if that's a bit of a mouthful, the authors realized. They say we are disturbed at the number of letters and syllables in the rather fanciful but highly appropriate name. And they suggest some alternatives. Some of them are actually quite funny. They have baleen, spherine, stockerine, or the carbo-sucker. But in the end, they decided, we'll throw it out there in the community, let the community decide. What stuck was the Fullerene. What stuck for the C60 in particular was the Buckyballs. So now that we have met the Fullerene family, let's have a look at how and where they fit in the universe. And so they're made of carbon, and that means they somewhere belong in this whole carbon recycling that's going on in our and other galaxies all the time, where stars like the sun, for instance, at the end of their lives, they shed off their outer layers. These outer layers are enriched by processes that have kept stars burning, and so they contain a lot of carbon in many cases. These get ejected into the interstellar medium. Interstellar clouds start collapsing to form new protoplanetary systems from which new stars emerge, and new planetesimals, asteroids, comets, and planets with possibly life on them develop. In this entire cycle, pretty much all stages, there are different types of chemistry going on. So first, the chemistry starts by turning atoms into molecules in these outflows of these stars. As the material cools down, you start forming molecules. First, simple molecules like CO, HCN, acetylene, that sort of things. But you can actually clearly follow much more complex structure than that. In dark clouds, you have a much more complex chemistry going on, which possibly may be relevant for prebiotic chemistry. And then there's probably more processing going on in these protostellar disks. Now, there's certainly a lot of chemistry going on. There's a lot of chemistry that we don't understand right now. And just one example about what's going on in this interstellar medium that we haven't figured out is a problem called the diffuse interstellar bands. Diffuse interstellar bands is a set where the latest surveys have counted about 600 absorption lines from the near UV to the near infrared. Not a single of these absorption bands has been identified to date. The first ones were discovered in 1922. Okay, and recognized as interstellar quite early on. And the only thing that happened in terms of characterizing the problem is people added more of these unidentified bands. Okay, and it's not that they're weak bands. Actually, some of these are quite strong. They're hard to miss. If you have any interstellar material in the line of sight, you will most likely pick up some of these absorption bands. We don't know what they are. They are most likely related to carbonaceous molecules, either carbon chains, for instance, or some of these PAHs, or maybe fullerene-related type materials. If you're interested in that, actually, Harold Linnertz, Nick Cox, and myself are organizing a conference on DIPS in the Netherlands next year in May. Now, by some coincidence, actually, the discovery of C60 and C70 was done in experiments that were aimed at addressing some of these puzzles in interstellar chemistry. It had been proposed that polyions, kind of carbon chains, were formed in the interstellar medium, and Harry Kroto didn't like that idea. He was sure that you could form them in the outflows of carbon stars, and they would actually be quite stable and survive into the interstellar medium. And so he joined a team at Rice University with Rick Smalley and Bob Curl, changed some of their experimental setup, and the whole idea that they had was, well, we're going to characterize part of the chemistry that's going on in these carbon star environments. And so they started from graphite. Graphite is another structure made of carbon atoms, where now you have different layers of these flat graphene type materials stacked in such a way that if you would look from the top, they kind of look like this. What they did is they vaporized the graphite, and they measured the size of the carbon particles that kind of fly off this graphite by using a time-of-flight mass spectrometer. And so if you do that, what you see is that you get a distribution in terms of sizes, as depicted right here. So you see that all sorts of clusters fly off of different sizes. There is a peak at about 60, but it's certainly not the only peak, and actually it's compared to the total, it's a small fraction of those clusters. However, this is taken at low helium pressure, so this is representative for the sort of materials that really fly off these graphite rods after vaporization. As you increase the pressure of a buffer gas, in this case helium was used, what happens is you'll get more and more collisions, and so what you end up with is something like a survival of the fittest in your laboratory experiments. And so what you see, as you increase the helium pressure, this is the way they manage to isolate these C60 and C70 species. You see that in the mass spectra, really the C60 peak now dominates. There's a second peak here at C70, and all the other species are far less common. And so this is weird because now, mind you, the researchers were thinking about carbon chains, long species. Why would there be a more stable species that has 60 carbon atoms, which is a chain, and nothing which is 58 or 62 or that sort of thing? So that didn't make sense, and they figured out that this must mean that a totally new structure is required. That's how they came to the C60 Buckyball. It turns out that for stability reasons, if you make these fullerenes, you don't want to have two pentagons right next to each other. You want to make sure there's a hexagon in between. You don't want to have touching pentagons. C60 is the smallest of the fullerenes where you can actually do this while satisfying all your chemical bonds. And so that makes C60 one of the most stable species. Okay. It also helps that it has this geodesic structure. So if you have a collision with the C60 molecule, actually it compresses a little bit, and it can sustain some pressure. And so immediately after this experiment, since this was done in the framework of what's going on in these carbon star environments, the researchers immediately in their paper suggested, well, you know what? It seems that these balls, they self-assemble in these carbonaceous gases. So if this happens in our laboratory, physics should be pretty much the same in space. They should happen in space as well. And so these species should be widespread and should be abundant in space. It was a prediction made in their 1985 paper. And so it makes perfect sense. And so astronomers went searching for these bands as soon as laboratory spectroscopy became available. And so the first thing to look for is for electronic transitions of these bands. Some searches were done for finding neutral C60, but no detection was claimed. It was said that this was not too surprising because in the end, if you think about the radiation field in the interstellar medium and the fact that the ionization potential for C60 is about 7.6 eV, you would actually expect, that most of the C60 would be ionized. A much more promising case was made for the ionized version of C60, the C60 plus, where two bands were found. This is an absorption band right here, second one right here. They were discovered, they're clearly interstellar in nature, and they are close to predicted wavelengths for C60 plus bands. You see they're slightly offset. This is still awaiting laboratory confirmation. The problem is that these wavelength positions are extrapolations based on a sort of laboratory techniques called matrix isolation spectroscopy that introduces unpredictable shifts in the bands. And so this is our best guess for what these shifts could be, but the only way to really be sure that these absorption bands are actually C60 plus is if we have a laboratory spectrum of cold gas phase C60 plus, and that is a challenge to obtain in the lab currently. So electronic transitions for C60 did not turn up any successful detection. We can also search at infrared wavelengths for the bands. At infrared wavelengths, typically molecules will be detected through all their vibrational motions, and as it goes in molecular spectroscopy, the more atoms a molecule is made up from, the more vibrational motions you have. And so for, oops, my text is gone. So for C60, hello. For C60, you in principle have 174 vibrational modes. So it's 174 ways in which these molecules can vibrate. As you see here, some motions involve torsional modes. Other modes like these ones, you actually change the radial distance of some of these atoms. In principle, there's 174 modes. They're not all unique. Different modes, because of the symmetry, will be distinguishable from each other. And in the case of C60, only 4 of the modes are infrared active, which means that those are the ones that in principle you can hope to detect. They're at 7 micron, 8.5 micron, 17.4, and 18.9 micron. Similarly, C70 has more carbon atoms, so it has more vibrational modes. C70 has 204 vibrational modes, and of those, 32 are infrared active. It has more active modes because of the reduced symmetry. Should also mention here that these wavelengths are the wavelengths for the neutral C60 species. If you would look at the vibrational modes for the cation bands, actually would see a different set of bands. So you can actually distinguish the vibrational spectra of C60 and C60 plus.
Yes. Those are vapor phase, though.
I'll get to that. There's small differences in the wavelengths between vapor phase and solid state, but I think the effects of temperature are much larger than that. So with this information, people went searching for the infrared signatures of these bands, and again, for a long time, we didn't find C60. Some searches were based on observations with the Infrared Space Observatory. More recently, kind of people were closing in on C60. Chris Selgren, for instance, showed that C60 was certainly a good candidate to explain 2 features that she saw in reflection nebula. There were some other candidates that seemed viable as well at the time. And so that's kind of the background against which we got a spectrum of a planetary nebula. Now, planetary nebulae are these dying stars. In this case, we're looking at a carbon-rich planetary nebula. They're beautiful. If you have seen some images and you say like, oh, these are gorgeous, chances are it's of these planetary nebula. This is the Helix Nebula. This is the Eskimo Nebula. What happens is that these dying stars eject their outer layers, and then you gradually expose a much hotter remnant of the star. And once it's hot enough, it actually ionizes this material around, and then that's lighting up all that material. And so these are carbon-rich if the star has produced enough carbon in its core during its lifetime and managed to bring it up to the stellar surface. And then on February 17th, 2010, a day which was supposed to be a quiet day, I had caught up on my administration, caught up on some research, was looking forward to a few days of not teaching and doing some research. And then one of my friends had this spectrum right here, which was observed by the Spitzer Space Telescope. And it wasn't clear what it was because it does not look like a typical spectrum for a planetary nebula. Now, there's a lot of good things about it. There's this dashed line indicates what is a thermal dust continuum. These narrow lines here are forbidden emission lines. Those are quite typical for planetary nebula. And I should say that below 10 micron here, we only have low resolution spectra. So some of these lines here are these forbidden emission lines as well. They just look broader than right here. Then there's a broad plateau right here, broad plateau right here. I'm not going to talk about those. There's some discussion about what those may be. But if you look at whatever features are left in this area of the spectrum, there's two strong bands. One was at 18.9, the other at 17.4 micron. And so this looked like C60, right? Now, if you make a model for C60, this is what you end up with. The red curve is a model for C60. The blue is a model for C70. And what I just done, skip from the spectrum to a model, actually was a few weeks of very hard work, lots of frustration, banging my head against the wall, for a variety of reasons that I'll get to in a minute. But in essence, when you look at these models, you see that there's a great correspondence between the intensities of the bands. And so with that sort of match between laboratory-based models and the observations, I think it's fair to say that the presence, the problem actually that we have is if you want to prove that this is C60, you have to go into the chemistry literature. The chemistry literature has lots of lab experiments, has lots of theoretical calculations about properties of these Fullerene bands. And it turns out that the exact wavelengths, the exact widths, and the relative strength of these bands are very dependent on, for instance, the temperature. Okay, so how can you actually figure out whether or not this is C60? Well, that's a whole story that requires some knowledge or some assumptions about the excitation mechanism. I'll get to that in a bit. But in the end, after a few weeks, we came to the conclusion that all the measurable quantities, which is wavelengths, widths, and the relative power, are totally consistent with laboratory experiments, at least if you use those laboratory values that are obtained at temperatures which are comparable to the temperature that we find for these molecules, which is about 300 K. Okay? If you would use laboratory data at 1000 K, you would find different results, slightly different results. And so in the end, we concluded that this means that the presence of C60 and C70 in space is firmly established. Since then, this was in July 2010, many others have confirmed these features in a whole series of environments. At the same time, there have been a few cases where it also turns out that our artist concept of the buckyballs around the planetary nebula could be recycled as well. So it's great. It's all carbon recycling. It's figure recycling. For instance, here's a paper by Garcia Hernandez et al., where they find more planetary nebula with fullerenes. So now it's no longer just one detection of these buckyballs in a planetary nebula. There's a whole series of planetary nebula. Some of them, in this case, in the small Magellanic Cloud, so in an external galaxy, not in our Milky Way galaxy. The same authors also found these buckyballs in many more planetary nebula in the large Magellanic Cloud. They also claim detection of this flat species there, which is planar C24, listing right here. I'm not entirely convinced by the detection. It should result in features along these red lines, and I'm not quite sure I can convince myself that I really see them. And in any event, these smaller flat type species are more related to polycyclic aromatic hydrocarbons. And what used to be across the road from here at NASA Ames, there's a whole group that's now hosting the largest database of infrared spectroscopic properties of such power molecules. They have a distinct set of features, which we see in some of these planetary nebula, but certainly not in all of these planetary nebula. If you like those graphics, by the way, as I found out yesterday, you can actually order magnets, fridge magnets, that show the buckyballs in interstellar space. Pretty cool. Did you get some money from that? No, I should talk to these people. It's, my research funding could use a boost, I guess. So. We've also found them in our Corona Borealis stars. Those are a different sort of stars. These are supergiant stars, which are hydrogen poor. That's important because a lot of the formation of fullerenes on Earth, at least for say moderate temperatures, can only happen in the absence of hydrogen. Once you have hydrogen in your experimental setup, then you don't form fullerenes anymore, but you form PAHs. And so for a long time, we thought, well, you need to form these fullerenes in hydrogen-poor environments. And so the obvious place to look for is in this sort of stars. They have already ejected their entire hydrogen envelope, but they are still carbon-rich. So we have found them in 2 of these Aurora Borealis stars. Surprisingly, we find them in the most hydrogen-rich of the Aurora Borealis stars. That's a bit of a puzzle, and it points to a need for reviewing our formation pathways. Here's a protoplanetary nebula. So now we're looking at an object which is not a planetary nebula yet. It's not reionizing all this material yet, but already we see evidence for the C60 bands. We also find it in, but these are still actually carbon-rich objects, so that all makes sense. We actually also found them in, oops, I think my laptop needs a moment. We also found them in these evolved stars. This is our planetary nebula, but these 2 objects here are binary stars, but they are oxygen-rich. So they have not dredged up enough carbon to become carbon-rich stars. You see typical chemistry for oxygen-rich objects, carbon dioxide production, yet in this typical oxygen-rich environment, where you also see things such as silicates, for instance, suddenly these carbon-rich molecules turn up. Okay? Again, we will need to review some of our formation theories. All those were evolved stars, so kind of where we think you actually form these fullerenes. They've also been detected in the interstellar medium, here in a reflection nebula by Selgren et al., here in the Orion Nebula by Rubin et al., and recently also by Boersma et al. And just a few weeks ago, a paper came out where we now also have solid detections of C60 in young stellar objects. And so if one thing is clear from these observations, we can actually reconstruct kind of the Fullerene life cycle. At least this part matches our expectations. You form the fullerenes in the outflows of evolved stars, typically. As I've shown, this can be oxygen-rich or carbon-rich, apparently. Exactly how this goes, we're not quite sure. They survive in the interstellar medium. We see them in the interstellar medium, and they get incorporated into protoplanetary disks. We see them in these young stellar objects. And so that's how they can become incorporated in comets and asteroids, for instance, and planetesimals. Okay, so then that's pretty much what we understand about the C60. So now let's say a few words about the things that actually we're either not sure about or we're totally clueless about. The kind of start, let's talk about the excitation mechanism. If you look at the spectrum, what you see is you see 4 bands that are emitting. One thing that I didn't put much emphasis on is this band right here at 7 micron. You see that there's a weak band in the model right here, but there's a strong band in the observations right there. When we were writing this paper, this band coincides in wavelength with a forbidden emission line by argon, and so the strength of this band was largely believed to be due to this argon line. I'm far less sure about it right now than I was back then, so maybe he made this wrong. It will turn out that this is actually a key point in the end, so we don't really know. But in any event, what we see is we see emission from these vibrational modes. So that means what we see in this simplified level scheme is we see downward transitions from an upper state to the ground state, okay? And so if you want to understand the emission that you see, what you have to understand is how you can get molecules in these excited states. That is what the excitation mechanism is all about. There's different ways of doing that. You can either do that by collisions. This is this highly idealized case of thermal equilibrium, something that we tell our undergrads as an idealized case. Really in space, certainly in the interstellar medium, there's very few environments where you would expect thermal equilibrium to actually hold. In that case, the populations of these different levels is determined by only one parameter, and that's the temperature. And so once you know the temperature, you can actually calculate how strong each of these bands should be based on how many molecules are in these states. Now, for large molecules such as PAS or fullerenes, what you expect is that a free molecule will absorb a UV photon, undergo an electronic transition to an excited state, and quickly transform that energy into vibrational energy. So it relaxes back to the electronic ground state, but it's left in a highly excited vibrational state, which would be off the charts right here. And then it cools down by kind of stepping down this energy ladder and emitting infrared photons. That process is called stochastic heating and fluorescent cooling through infrared emission. And you would think you could easily separate those two processes. Certainly if you look at some models, this is a model for this process of stochastic heating and fluorescent cooling. In white, you see a low energy photon being absorbed, 3 eV. In blue is 15 eV, and then there's others in between. First thing you should notice is that these two bands are highly insensitive to the exact photon energy that you have. All variations happen in these two bands pretty much. And here's a close-up of those two bands. Again, hardly any change in these two bands, but between these two bands, you can actually see that for different photon energy, you get very, very different band ratios. Okay, if we compare these to our observations of our planetary nebula, what we see is that the two ratios that we can reliably measure, where there's no contamination by this argon line, they don't really match the typical sort of energies that we would expect. Okay, the ratio of these two bands, which is insensitive to the photon energy, we measure is about 0.6, whereas all models say it should be 0.27, 0.28. Okay, so we're off by a large amount. This band as well can be anywhere from 0.29 to about 0.58. What we measure is 0.27. Okay, if really this means we're talking about fluorescence, it means that the average energy that these fullerenes absorb is below 3 eV. Now we know that all these molecules have very strong electronic transitions in the UV and the near UV. So why would they not absorb any photons at those energies? For a star with effective temperature of 30,000 K, there are plenty of UV photons around. So it doesn't really add up. If you look at thermal excitation, what you see is that for temperatures, say, between 50 and 500 K, you see big changes in the ratio of these two bands. And actually, if you want to see these shorter wavelength bands at all, you need to be at temperatures higher than about 200 K. Okay? And in the case of thermal excitation, if you make a plot where you plot on the y-axis the total emitted power and the x-axis the energy of the vibrational levels, in thermal equilibrium, what you would expect is that all these points fall on a straight line, and then the slope of that line is inversely proportional to the temperature. Actually, we did this for our planetary nebula, and much to our surprise, it turns out that for both the C70 bands that we can measure and the C60 bands that we can measure, it seems as if they're falling on a straight line. So it seems as if they are in thermal equilibrium. The one outlier is this guy right here. And so for our paper, we assumed that even though this is way off our line, we assumed that most of the flux in that line comes from this argon emission, right? I'm far less sure, and if this really is somewhere around here, that basically would mean that it cannot be thermal equilibrium as well. In any event, if you do this, you determine a temperature of 179 K for the C70 molecules and 300 K for the C60 molecules. Now you have one parameter to make a model. If you use that one parameter for your model, well, actually it's two, one for C60 and one for C70, then you end up with these models. And so these compare quite well to our observations. Okay. And so we are actually hoping that we can come up with some excitation diagnostics, but it's not quite that simple and straightforward. The problem is that if you look at band ratios, for instance, what you see is that these dashed lines would correspond to a series of thermal models, and these, the solid lines are thermal models, the dashed lines are fluorescence models. They're close to one another. Second thing to note is there's 3 different sets here. Those correspond to different laboratory measurements or theoretical calculations. Okay, so it seems that it's hopeless right now because I don't know which of these laboratory data are theoretical calculations is more reliable than one another, okay? And so depending on which value you use, you get very different values for these band ratios. These crosses indicate measured values in our astronomical observations for a few cases where we think that there's not an awful lot of contamination by anything else. And so there's not a single curve that's consistent with these observations right now. And so at this moment, we're not sure whether we're really looking at thermal excitation. We're not sure whether we're looking at fluorescence. Okay. And so this is kind of a summary of the surprises and issues that we found when we looked at our star. We saw that they were neutral. That's not quite what we expected. We saw that they were cool in the sense that we didn't see very strong emission at the shorter wavelengths. A few other things that for us were a bit strange. And so we actually put in our paper that it seems clear that these cannot be free C60 molecules in the gas phase. Okay, that's just the hypothesis of free molecules in the gas phase is not compatible with our observations at all. And so that's pretty much why I was a bit surprised 2 days ago when this press release came out about Spitzer finding solid buckyballs in space. It's of course slightly different. We said that it cannot be in the gas phase. That's not quite the same as saying that you're talking about solid C60. This actually immediately reminded me that was probably an engineer that made this drawing or something. I don't know, it's like close packing of a ball. How do you calculate this sort of things? And then how do you explain this? You put them in a crate and you ship them. So who put this crate of buckyballs out there? I don't know. This is now on NASA's website. Key message for this thing is that this is a great source of vitamin C60. So keep eating your fullerenes. So I'll skip this for now. So I think that indeed they're not in the gas phase. One of the exciting possibilities that we've been kind of keeping in the back of our head is you can actually make small crystals with C60. And so those crystals, if you measure the spectrum, they have the same 4 characteristic bands. Okay, the same sort of vibrational modes. They just have a much larger heat capacity. And so for us, that would explain how you can have fluorescence that seems to correspond to a fairly low average photon energy. And then the last thing that I quickly want to go over is problems with the Fullerene Formation mechanism. If you look at how you make fullerenes in the lab, the original experiments by Kroto, for instance, the gas that you have needs to be carbon-rich and hydrogen-poor at the same time. Now, in most astronomical environments, there's a lot of hydrogen, okay? And there's not an easy way to get rid of your hydrogen. In our planetary nebula, where we detected them, it turns out there's actually hydrogen in the stellar photosphere. There's hydrogen all the way around. Somehow we missed that when we wrote the paper. So there is hydrogen around. And so this sort of mechanism where you need to have a hydrogen-free or a hydrogen-poor environment seems to be at odds with that, with those observations of hydrogen. So you need some alternative. One alternative that has been put forward a few times by notably Garcia Hernandez et al. Is that what we're looking at may be photoevaporation of hydrogenated amorphous carbons, kind of the standard form of carbon in space, we think. If you look at experiments where you do these sort of photoevaporation measurements, you see that you do indeed produce small amounts of fullerenes, but you produce much more PAS, and you also produce much smaller carbon molecules and fragments. We don't see any evidence for those smaller fragments, and actually we see a lot of sources, or we see a few sources where we have only fullerenes and no PAHs. So you need some additional processes then to get rid of these PAHs, and it's not quite clear how that would work. Moreover, if you look at some observations, what you see is that the C60 seems to be not co-spatial with the PA emission that we see in those sources. So if they originate from the same Hugg species, kind of hard to explain this sort of distribution. An alternative is to form at high temperatures. If you do combustion experiments at temperatures of 3,500 K and higher, even in a hydrogen-rich environment, you will form fullerenes and you will not form PAHs. However, that seems way too hot for the sort of environments that we're talking about. And then you could also think that you could form fullerenes from PAH destruction. You have PAS here. As you get closer to the star, some mechanism could transform the PAS into fullerenes. It's something that's been worked out for the interstellar medium by Bernet and Thiens. And for the interstellar medium, it may work. However, if we plug in our parameters for planetary nebula, that doesn't work at all. That mechanism is not viable. And so the conclusion is that we need a different route for the formation of fullerenes than anything that we know about right now. And so several people are working on that right now. So that's pretty much what we know. We really need to figure out these things, though. The excitation mechanism, we need to figure out whether they're in the solid state or they're in the gas phase. So if you or somebody you know has very good laboratory data that we could use, please let us know. It would be very useful. The main reason why a lot of people are excited about these fullerenes is not just because now, after 25 years, we can say, see, told you so, we're right, we understand chemistry, carbon chemistry in space. It's actually the first large aromatic species that we find in space. If you think about PAHs, typically about 10–15% of all the carbon in the universe is supposed to be in the form of these PAHs, but we don't know exactly what sort of population of PAHs exists in space. These fullerenes, they share a lot of properties with these PAHs, and certainly with some of the spectroscopic observational properties that we have. And so we can use the fullerenes to study PAHs in space. Things that are relevant for fullerenes are probably also relevant for PAHs. And so even for some of the formation mechanisms, if we figure out how fullerenes are formed in space, well, we should probably see whether a similar mechanism is relevant for PAHs as well, for instance. Then there's all sorts of exciting things to do with fullerenes. If you ionize fullerenes, you can actually throw an awful lot of stuff at them, and it kind of sticks. So you could use fullerenes, for instance, to do all sorts of surface catalytic chemistry. You could put things in the fullerene cages, and so maybe that sort of structure could, in the end, be responsible for some of these diffuse interstellar bands that would make things full circle. And so let me end there. Again, take home message. I think that the presence of C60 and C70 fullerenes in space is now firmly established. They're neutral and cool, which we didn't expect, and we're not sure about formation, their state, and their excitation mechanism. Thank you. Let me thank my collaborators, actually. There we go. Yes.
Jan, could I just kick off with the questions?
Sure.
The initial detection, you had this dust continuum. What was the temperature of the dust, and did
it's cold. It's about, I believe, 100 or 200 K. It's not the same temperature as the fullerenes.
And not even the C70?
Not quite, no. Okay. And actually, the one slide that I skipped is kind of relevant for that one as well. It's this one. If you look at the dust continuum, this black line here is the dust continuum that we see in our planetary nebulae, and so it's it's at the center. This yellow curve is where we see the C60 emission, and so they're not at the same spot as where we see the dust emission from. So, and this is actually very surprising because it turns out that they're about 8–9,000 AU away from the central star. So that distances you can actually still excite them, would point to fluorescence, or you would think of fluorescence, but then we don't understand how you could do that with these low energy photons. So.
Hi. On one of your slides, you had the temperature of C60 at like 193 Kelvin and the temperature of C70 at 300 Kelvin. How is it that, are they side by side in the same planetary nebula, or how is it they're such different temperatures?
We're not sure, is I think the honest answer. What we basically do is we determine a temperature based on this excitation diagram. And so an excitation diagram really only tells you the actual temperature if you're in thermal equilibrium. And these sorts of environments, there should not be thermal equilibrium. So I have a hard time understanding that part. But if you take what gets out at face value, you find that the C70 is colder than the C60. If that's true, then you could think of different ways of explaining it. For instance, by first forming the C60, and as it sails out from the C60, forming the C70, for instance, and it would be located further out, it would be a little bit colder, but I'm not quite sure whether that would really work out if you do the calculation. So I don't know.
Back starting in, I think, the 90s, Becker et al., when they first claimed to find fullerenes in meteorites, even though the papers, I'm pretty sure, were in Nature, those, if I remember correctly, quite nasty reactions to them. Becker et al. Said the helium-3 to 4 ratio was extraterrestrial.
Mm-hmm.
And a lot of people didn't like that. I don't see how it got in Nature with some of the remarks I heard. But what do you think of, and maybe what also has that got to do with the temperature, the helium ratios that they were finding in the buckyballs?
Well, so I know of the paper, and we could start a whole discussion about how to get papers in Nature, I guess. But I think the key point is that I have not seen any independent confirmation of those results to begin with. So I'm not sure about where those measurements are really true. The ratios that they measured, I'm not sure whether they're related necessarily to the temperature of the fullerenes, but the whole idea was that the isotope ratios correspond not to solar system values, but to interstellar values. And so the whole idea was that you would form these fullerenes outside our solar system. You incorporate these helium atoms inside, and you just keep them trapped until they land on the Earth, pretty much. So, does that answer the question, or?
Well, if the helium-3 to 4 is real, let's say, then as far as your proposed mechanism,
If it's real, I think the only thing that you can say is that it's extraterrestrial or extra solar system in nature, really. Yeah.
Okay, we have one question by myself. First, I would like to congratulate you for giving a talk about spectroscopy and making it fascinating, because I know that's very difficult. There is no pretty images, but this was very good. My question is about the search for buckyballs. Is anybody have been trying to find buckyballs around minor bodies, specifically comet or carbonaceous chondrite asteroids?
Yes, I think there's been some attempts to look for them in comets, but I don't think they've been found. So.
Okay.
They have been found in meteorites, though.
In meteorites,
Yes.
have been found in laboratory.
Well, I think there were two papers, right? There was a paper about the helium ratios, and there was another paper about the fullerenes in the KT boundary or something. I don't know whether that was.
There were more than two. There was actually several.
I have a basic question here. Carbon is valence 4, but in these buckyballs it only has 3 neighbors. So there's a loose valence on each carbon. So what happens to that in the lab? And I think the last slide gave some ideas as to what happened to it in space.
I'm sorry, I'm not sure whether I understand.
No. So, well, all these carbon atoms have 3 of their valences tied up with neighboring carbon atoms in a buckyball, and they have a 4th valence that's loose.
Well,
So
they
what-
form aromatic
They're double bonds.
structures. Yeah.
But they're double bonds, so it's not a loose valence.
Yeah, that's right.
Okay. But it could become detached from the loose double bonds to become.
Well, you can do things to your fullerenes to actually break
Uh-huh.
the bonds, or you can
You
attach
can
hydrogen
do-
to it or something. Yeah.
But it's not like they're end up with hydrogen in a lab or anything.
No, not the ones that I was talking about.
Jan's gonna be here later this afternoon, so you can talk to him. One more question?
I have a question about, in your discussion of the formation of these materials, somehow the word thermodynamics hasn't come up. I mean, has anyone dealt with just essentially fundamental thermodynamic reasoning as to how much hydrogen, for example, it would take to eliminate buckyballs, or the conversion of graphite to buckyballs in the presence or absence of hydrogen? It seems to me that there are values available in the literature to at least establish some boundaries or some stability regions for either graphite on the one hand or C60 on the other.
I'm not sure. I mean, it's not something that I've been searching for an awful lot. What I do know is that researchers already have a hard time to explain on say the on a step-by-step basis how you can make those fullerenes. And so even in the experiments of Croto, for instance, you have all these collisions going on. And so certainly, you can think of an equilibrium sort of situation, but what are the chemical pathways where you go from smaller clusters to the larger ones, or from the largest to the smaller ones? And that exact chemistry, I know one paper where they've tried to do it with molecular dynamics calculations. And so what you see there is that you start from much larger structure, and on very short time scales, you actually kind of kick out carbon atoms and then make your buckyball cage. The rest I don't know much about.
I'll get your card and send you some.
All right, thanks.
Yeah, and naively, some of the structures you showed earlier, the onion and the jug or bottle, whatever it was, have some properties of living cells. Is it possible that buckyballs played some role in the origin of life, the cell structures that somehow morphed into life?
There's certainly been claims, but to the best of my knowledge, I don't think it's backed up by experimental work, for instance. So.
And one other quick thing, you mentioned laboratory measurements and stuff. Is X-ray crystallography used at all to study buckyballs?
It's used to establish this crystal structure of the C60 crystals, but I don't think it's being used for the gas phase species. One of the cooler experiments on fundamental physics that have been done on C60 is it's one of the larger species that has been used to show the wave-particle duality. So it's like you kick a ball around to keeper, and actually there's two balls, and you score in both ways, something like that.
The reason I ask is that at SLAC and other centers, there's been a breakthrough in the intensity of X-ray systems that can be used for crystallography, and they can actually have such an intense beam they can study individual atoms with what used to be called crystallography, but it's just an individual atom. If that was of any use, it might be a way to think about it.
Thanks.
Last question.
This is probably fundamental chemistry, but my question is, why don't carbon atoms form smaller clusters like C12, for example, where the carbons would be in a, I guess you'd call it a cuboctahedral structure, where you got 6 in a ring and then 3 above and 3 below?
Yeah, that's fundamental chemistry. More that's not my my area of expertise. I'm not sure. I mean, kind of just about understand that C60 is the smallest one where it can fulfill all the valences in the structure of pentagons and hexagons. But you can actually make smaller buckyballs, but you lose the stability of the species. I think the smaller species tend to form more the flat type molecules.
Yeah, the small ones, I guess you'd have to bend the bonds too much.
That's right. They just wouldn't be stable.
All right.
C60 has just the right geometry to provide the stability that the molecule needs to exist.
All right, Jan, we have a Are We Alone mug for you. Unfortunately, it's not made of Buckypaper, but maybe you can put some Buckyballs in it or something like that. So please join me in thanking Jan for his great.
Thank you.